We're going to look at rational functions and determining the numbers at which a rational function is continuous. We're going to use limits to analyze the graph of R and then look at R by graphing R. And the first one, we're going to do 5 problems here. And the first one we're going to do is this first rational function that you see here. The thing you need to remember is the property, the limit of a quotient. Okay, so that's the property of the limit of the quotient here. And the first thing we're going to do is factor R of x. So you factor R of x, what we find, this is going to be x minus 2 over x minus 2 times x minus 4. Now from algebra, pre-cal or algebra 2, you should know that the domain of R is all real numbers, with the exception that x cannot be 2 and x cannot be 4, because you cannot divide by 0. If you plug these numbers in at the denominator, you get 0. So this means, based on our definition of continuous functions, that R is discontinuous. I can't spell, but discontinuous at 2 and 4. But we're going to use limits to analyze what's going on there. Okay? And I still spelled this wrong. Discontinuous. You know, math people can't spell very well. All right. Now, so R is continuous everywhere else but 2 and 4. Now we want to determine the behavior of the graph near 2 and 4. So we're going to look at the limit as x approaches 2 of our function, rational function. And we're going to look at the limit as x approaches 4 to see what's going on there so we can graph this. So for the limit of x as it approaches 2 of R of x, we get the limit as x approaches 2, and we're going to cross these two out here, and we're going to get 1 over x minus 4. You plug in the 2, and you're going to get negative 1/2. So as x gets closer and closer to 2, x gets closer and closer to 2, then the graph gets closer and closer to negative 1/2. That's what the limit means. It's not defined there, but what we'll have is a hole. So the hole's going to be where x is 2 and y is negative 1/2. There's going to be a hole there. All right, so let's do the limit of the 4. So it's the limit as x approaches 4 of R of x. We have the limit as x approaches 4 of 1 over x minus 4. And we're going to see that if x is less than 4, it's going to be 0 if you plug in 4. But if x is less than 4, x gets closer and closer to 4. And the value is negative, and it becomes unbounded. So basically we're looking at the limit as x approaches 4 from the left. And so all numbers smaller than negative 4, or than 4, so 3, 2, 1. And when you plug that in of R of x, you're going to get negative infinity. All right? Because it gets smaller and smaller and smaller. But it's negative. This is going to go negative. So if, for example, if I plug in 3, that's going to be 1 over negative 1. If I plug in 2, it's going to be 1 over negative 2. If if I plug in 1, it's going to be, so it's going to get smaller and smaller, and it's going to go to negative infinity. Now, when we approach from the positive side, and so if you put in 5 in here, and 6, it's going to go to infinity. Okay? So basically that means the absolute value of r of x will go to infinity for x close to 4. So basically, let me graph this. So what we have is, here's our 2. There's a hole at 2. Let me move this over a little bit. We've got, let's put 2 right here, and then make this negative 1/2. We know there's a hole here. There's an asymptote at 4. You can't have both a hole and an asymptote, so we have a asymptote here. And this is what's happening to the graph. Keeps closer and closer. And the asymptote here at 4 goes like this. Something like this. And this would be, say, 6. Would be here. Alright? So if I look back at what we talked about here, as x gets close to 4, it goes off right here to infinity. Alright? This is going to negative infinity. And this one, as it's going from the right, and this is negative infinity down here, and this would be infinity, and up here would be infinity. Okay? Alright. Now let's do, we're going to try to do 4 more problems if they don't take too long. We're going to do, the next one we're going to do is r of x equals x minus 1 over x squared minus 1. And we're going to evaluate the limits at c equals negative 1 and c equals 1. Because when we factor this, we're going to x minus 1 over x, sorry, I'm doing the wrong thing, x minus 1 times x plus 1. So the first thing we're going to do here is look at the domain. So the domain of R is x, but x cannot equal 1. And if you don't mind, I'm just going to put plus or minus 1 here. Can't equal plus or minus 1. So that means it's continuous except at 1 or negative 1. So we're going to say R is discontinuous at 1 at plus or minus 1. All right? Now, we're going to look at the limit as x approaches negative 1 from the left. And when you're looking at that, we're looking at f of x, which is really 1 over x plus 1. And when you plug in, say, we're looking at negative 1, negative 2, negative 3 into this value, this is going to get closer and closer to negative infinity. So it goes unbounded to negative infinity. All right? So basically, we're saying as x is less than negative 1, 1 over x plus 1 is less than 0. As x approaches, I'm going to just write I'll write it out, approaches negative 1. So this becomes unbounded. All right? Now let's see what happens when we take the limit from the right side. We're going to take the limit as x approaches negative 1 from the right side of r of x. And when you do that, you're going to get this equals 1 over x plus 1, and it's going to be infinity. Because if x is bigger than -1, then 1 over x plus 1, and you can plug in some values. So plug in 0, plug in 1 and 2, it's going to be bigger than 0. That means x, as x approaches -1. So 1 over x plus 1 becomes unbounded. All right. There's also a whole when you plug in 1, so we're taking the limit just as x approaches 1 of 1 over x plus 1. And once you plug in 1, you get 1/2. So there's a whole at 1 comma 1/2. Okay, so I'm going to graph this. When I graph it, I know I have an asymptote at -1. I have a whole at 1 -1/2. You should already know how to graph some of these rational functions. So we're going to go down here. I'll just make this, is that -6? And 6, say. And then it's going to come through here, cross at 1, sorry. And cross at 1. And you get the idea. All right, so this would be about 6 and -6. Okay? And I think you've done this before in pre-cal, but you just didn't call it. You used different words. So we already knew how to find wholes. This is going to -infinity as we're approaching x from the right. Then from the left, it's going to -infinity. Well, from the right, it's going to infinity up here. Okay? And this would be infinity here. Okay? The next one we have is r of x equals 3x plus 6 over x squared minus 4. I'm going to go ahead and factor this. 3 times x plus 2 over x minus 2 times x plus 2. I almost think it's better to graph. We know the domain is all real numbers. However, x cannot be plus or minus 2. Therefore, it's r is discontinuous. At plus or minus 2. Now, it's either going to have an asymptote or a hole there. So what we're going to look at is the limits. We're going to look at the limit as x approaches 2 from the negative side. And when you cancel this out, you're going to get 3 over x minus 2. So when you take the limit here, meaning all numbers from the left of 2. So from the left of 2, that would be 1, 0, -1, and so forth. And that's going to approach -infinity, because when x is less than 2 and you plug in values in 3 over x minus 2, it's always going to be negative as x approaches 2. And so it becomes unbounded. Becomes unbounded. All right, now let's try the limit as x approaches 2 from the positive side of r of x, and which is 3 over x plus minus 2. Again, you should plug in values, because when x is bigger than 2, then your value here is going to be greater than 0, or positive, as x approaches 2. And also you should notice that 3 over x minus 2 becomes unbounded. All right. Now, When you plug in -2, you have limit, so x approaches just -2 in general. We get 3 over x minus 2. That gives us -3/4. So that means there's a hole. When x is -2, y is -3/4. And it's not doing it for me. -3/4. So let's graph this. We have an asymptote at x equals 2. All right. And a hole at -2, -3/4. So right about here. A little higher, I guess. And then you should know how to graph a rational function here. Okay. And this goes here. And then you can see the limits. You're taking limits. This is infinity, negative infinity, negative infinity, and infinity. So as x approaches from the positive side, so we're going this way, we're going to infinity. As x approaches from the negative side, we're going to negative infinity. So we're going to infinity here, negative infinity on this side. Okay? Now let's try one more, because this video is getting just too long. I was going to do an extra one, but let's see if I can find a different kind. They're all about the same, so let's do one more. So here's our function, our rational, x squared plus x over x squared minus 1. And we have x times x plus 1 over x minus 1 times x plus 1. And so the domain, this is going to tell us where it's discontinuous and where we're going to take our limits. At negative, it can't be plus or minus 1, because if you plug 1 or -1 here, it'll give you 0. And that means you have vertical asymptotes or a hole. Now when I reduce this, I'm going to get x over x minus 1. At 1, positive 1, it's going to be a vertical asymptote. But when you plug in -1, you're going to get a hole, because you get a amount there. So what we're going to do is take the limit as x approaches 1 from the left of r of x, and that's going to be x over x minus 1, and that's going to go to negative infinity, and the limit as x approaches 1 from the positive of r of x, as x over x minus 1, that's going to go to infinity. Okay, because it's here we have when x, on this part right here, when x is in between 0 and 1, because it can't equal 1, x, erase this, x over x minus 1 is less than 0, and as x approaches 1, it becomes unbounded. And this one, the same thing. When x is greater than 0 or greater than 1, x over x minus 1 is positive, so it becomes unbounded. These become unbounded. All right, so let's look at the holes. Since we can use -1, let's take the limit as x approaches -1, x over x minus 1. Since this is defined, we get 1/2 when you plug in -1. So there's a hole at -1, 1/2. And we can graph accordingly. We have a, since the degrees are the same, let's go back. Remember this, when the degrees are the same, we have a vertical asymptote at, you divide the lead coefficient. So we have a horizontal asymptote at y equals 1 here. We have a vertical asymptote right here, and that's where it's undefined, at x equals 1. We have a hole at -1, 1/2, which is about here. And then you just kind of draw your characteristic graph. That's what you're doing. Draw your characteristic graph. And it would look like this, something like this. I'm going to change colors real quick. Basically, it looks something like this. Okay? Now, after I draw the graph, you might want to go back on the video and look at how we did limits. So this, remember, as x approaches from the right here, we're looking on the far right. As x approaches the right, we're going to infinity. As x approaches from the left over here, we're going to negative infinity. So that's the limits there. The next video is going to be on piecewise functions and where they're continuous and how to determine if they're continuous.